So now what I want to do is I want to give you an example of the timing analysis for a circuit. So this is again here, you're going to see that this is basically my R1 and this is basically my R2, the register 1 and register 2. And my combinational this time, I specified what my combinational logic is. And I gave you a few specifications, and these specifications are for the flip-flop. So I gave you a bunch of numbers. So this is the clock to Q for the contamination, which is the fastest, and the propagation delay for the clock to Q, but not propagation delay, propagation clock to Q, which is 80 picoseconds. And then you have the setup time and the hold time. And here what I'm doing is I'm telling you each one of these gates have the following. They have a contamination delay of 25 picoseconds and the propagation delay of 40 picoseconds. So the fastest response they can give you is 25 and the slowest response it can give you 40. And I just copied these equations in here so we can actually write them or use them here. So what we're after here is we want to compute the maximum clock frequency that this particular circuit can operate in, and we want to make sure that the whole time constraint is actually satisfied. So we're going to get started with calculating basically the maximum frequency. So we want to figure out what the maximum clock period or clock frequency. So in order for me to do this, what I need is I have the per gate propagation delay and contamination delay. However, my combinational circuit is actually bigger than that. So generally speaking, what you need to do is you need to figure out your shortest path between these gates and the fastest path. And if you take a look at it, the shortest path is actually here or here. These are the shortest path in that circuit. So if C change, you're going to see that basically X prime, or if D change and Y prime, they change basically after one gate. That's the shortest change that it can happen. So technically speaking, the total contamination delay is actually just 25 picosecond. Okay, that's the fastest response that you can get from an input in here to an output in here. That's the fastest you can get. Similarly, you can think about it in the following way. Let's figure out the longest path on this particular circuit. The longest path is an A changes, and then C changes, and then D changes. All of them change. So this is basically the longest path you can take. So in order for you to get a signal from here to here, you're going to have to go through 3 gates. That means the total propagation delay, which is basically the slowest, okay, that's the slowest, is going to be 3 times 40, which is basically 120 picosecond. And that's basically the total propagation delay. Not that, it's a little bit different. We can call it, for example, total, if that makes you a little bit more comfortable. Okay? All right, so what we need to do is we need to figure out the TC by just plugging in these numbers. So we're going to figure out that TC is actually must be greater than or equal to propagation clock to Q, which is this one here. This is 80. The propagation delay, which we just calculated to be 120, and the setup, which basically is given to be 50. So technically speaking, that T of C should be greater than or equal to, this is basically, I think, 250, that's what I think, okay, 250 picoseconds. Okay, and of course you can basically figure out what the clock frequency, and you're going to get about 4 gigahertz, okay, by just taking the reciprocal of that. So the maximum frequency that this particular circuit can operate at is 4 gigahertz. Okay, good. So now what if I actually want something, what about the hold time, for example, the hold time violation? Is it violated or not? Let's figure it out. So what I'm going to do is I'm going to say T hold, which is, I believe it's 60. It's telling me it's less than or equal to T CD, which is 25 picosecond, plus T CCQ, which is 30. Well, obviously 60 is not less than or equal to 55, so apparently the hold time is actually being violated, the hold time constraint. So you need to actually fix it. So if you operate the circuit, you're going to get hold time violation, so you're going to get metastability. So we need to fix it. So one quick fix here is the following. So what we can do is, and you can compute this all in, like at home as well, but you can see what I did is I actually added a couple of buffers in here and a couple of buffers in here. Okay, again, so what happens is, like with a hold time violation, it gets violated if the circuit is too fast. So what we need to do is we need to slow it a little bit. So I'm slowing it by adding buffers. So what I'm doing right here is effectively I'm just making my shortest path, which was here and still is here, at least in this case. My shortest path now passes through 2 gates, so that means my total contamination delay now is not 25, but it's actually 50 picosecond, but I'm going through a couple of gates, that's why. Okay, Let's see if actually the propagation delay, you need to actually think about the propagation delay. It's still that 3-1. Sometimes adding these buffers actually change the propagation delay, so it changes the maximum frequency as well. It just happened in this case, it does not, so that's fine. So now we can figure out the t-hold basically the whole time, whether it's violated or not. I'm going to see 60, is it less than or equal to the CD, which is 50, plus TCCQ, which is 30, and 60 is less than or equal to 80. Yes, so the whole time have been fixed. So generally speaking, you're not going to be doing, when we're doing FPGA, you're not going to be doing this setup time and hold time corrections. It's actually the EDA tool, which is Vivado in our case, would actually do this. And as you probably know from any digital logic concept, is actually the more logic you have, the faster the system would have. Like generally speaking, it's like, of course, if your design happened, like if you want to make something a little bit faster in terms of combinational circuit, you just need to add a little bit more logic. So more logic, it translates to FPGA that you need a little bit more area on the FPGA. So this graph is showing me the following, that the more area you use in here, okay, the less the delay it will be. So there's some sort of a graph that will happen. So if you design something and you're trying to run it and the EDA tool detected that some sort of a setup time or a hold time violation, it'll actually try to fix it by synthesizing a little bit of a different version in here by using a little bit more area. And this is usually done automatically for you. You just have to specify and figure out that your hold time and the setup time are actually not violated by actually looking at reports in Vivado.